Hello, I'm Virgil Goldberg, and this is my Lab 4 on oscillation. So, as a little introduction, the aim of this lab will be to compare real and simulated motion of a mass spring system. So, it is in a non-linear motion, but on a 2D plane, so only movements in the x and y axes. And we'll see that with the results, that there's a slight difference between the real and simulated motions due to several environmental factors. So here are the key concepts of this lab. So first, there's obviously Newton's second law, always here, the momentum principle with the position and velocity updates. We also have the energy principle, which is the energy, and this means that the energy of a system does not change without any external work or force acting on it. And the energy is equal to the force times the displacement. We have so within the energy principle, we also have the gravitational potential energy, which is the potential energy due to the Earth's attraction to an object of non-zero mass. There's also the spring potential energy, which is the potential energy stored by a spring. And finally, we have the kinetic energy, which is the energy of an object due to its motion. So here are the different formulas. We can see the Newton's second law, the energy principle, the potential energy, kinetic energy, and of course the respective force equations of all these energies, which is of course these without the displacement. So here is my experimental tracking. So the initial conditions of the mass spring, it started in the hand of this scientist with a velocity of 0 at position x minus 0.104 and y minus 0.630 with a mass of 0.4 kilograms. You can see that this here, the value is not there, but is 70 centimeters. And with the results that we could have found by doing a system of equations is that gravity obviously is 9.81, but the K constant of the spring is of 6.85, and the relaxed length of the spring is of 0.127. So for the computational model, here is the code. So we have obviously the mass of the ball here and the initial conditions that we found here previously. So we also have the gravitational constant, the spring constant, and the relaxed length that we've also found previously. Here we have, here it shows how to find the length of the spring, the direction, and the magnitude of the displacement. Here we have how to find different energies as well as the sum of the energies at the bottom, which will be important later on. Here we have our force updates and also our position and velocity updates as usual. Here finally is to print out the different values for energy. So here are the differences between the computational results and the model results. So we see that when it comes to the y-axis, in the experiment there was less amplitude. It would drop about the same amount but not rise to the same level. So this could be due to several environmental factors such as air resistance, that the spring is of course not perfect and is attached to something, and there's friction losses. Now here with the x on the x-axis, we have a way more consistent and similar curve, but we see that it seems that the experimental value is slightly shifted. So this could be due to a slight initial velocity in the mass that I did not take into account or could not find, which would explain this little shift to the left of the experimental graph. So for the extension, first our question is how can we see that how does the energy principle stay true? Well, we can see from this graph, which graphs all the energies including delta E, which is the change in energy. We can see that it is at 0 constantly. That means that the energy before and after is the same, hence the energy principle is maintained. There is no loss in energy, no loss or gain in energy. Of course, in real life, we know that this is slightly wrong because there's obviously air resistance, friction, and other outside variables. So when it comes to the period, if we use the x-axis, we found 1.7 seconds about, and if we use the y-axis, it's 1.5 seconds. So slight difference, not huge, but this can be explained by several things, once again, air resistance, friction, all of that, but also very possibly due to an initial velocity. Of course, if there was a slight velocity towards, for example, the bottom or the top, it would explain a slightly lower or higher, even y-axis or x-axis period. Thank you very much.